All right, so welcome back to the second talk. So we have Joy Hamlin from Rutgers University telling us about hook multiplication in the quantum K-theory ring of the Grassmannian. So please take it away, Joy.
Yes. Hello. So setting up some preliminaries and notation. I'll write X for the Grassmannian of M planes in n-dimensional complex space. I'll write P sub X for the M by n minus M rectangle that contains partitions that's associated to the Grassmannian. My T-fixed points are E sub lambda, and that's the span of EI where the ith step is vertical as you go from the lower left to the upper right. I'll write B for my Borel subgroup of upper triangular matrices and B minus for the lower triangular. And Schubert variety notation, X lower lambda is the action of the upper triangular matrices on E lambda. X upper lambda is the action of the lower triangular matrices. This notation choice gives us the dimension of X lower lambda equals the codimension of X upper lambda equals the number of boxes in lambda. And with square brackets, those represent the classes that form a basis for the cohomology. Um, Cohomology can be generalized to quantum cohomology, where cohomology counts intersection points, quantum cohomology counts intersection curves. I have the moduli space of degree d, genus 0, three-pointed curves in X. This can be thought of as the functions from the projective line to X of degree d. Note that the projective line is of genus 0 and has three marked points, 0, 1, and infinity. Given partitions lambda, mu, and nu, we can look at the Gromov-Witten variety of degree d to be the degree d curves that meet x upper lambda, a translation of x upper mu, and x lower nu as a subspace of this moduli space. It might be that there are finitely many such curves. If that's the case, then the Gromov-Witten invariant is the number of such curves that exist. If there aren't finitely many, then this invariant is 0. And the Gromov-Witten invariants give us the structure constants for quantum cohomology. So as a z adjoin q module, it's z adjoin q tensored with the cohomology. And how does quantum multiplication work? It's exactly the degree d Gromov-Witten invariant as the coefficient on q to the d x nu. Note that in the d equals 0 case, a degree 0 curve is just a point. So you're counting degree 0 curves that meet all three is counting points that meet all three. So this is doing the same thing as standard cohomology in the degree 0 case. Another generalization of cohomology is K-theory. The K-theory ring is the vector bundles over X up to short exact sequences. If we want a basis over Z, we can look at the structure sheaves of X lower lambda or X upper lambda, whichever you prefer, and I'll be writing O up or down lambda without the square brackets to denote that class. K-theory multiplication is fully understood. We have a combinatorial Littlewood-Richardson rule for it. We know how K-theory multiplication works. We can generalize in both directions at once and get to quantum K-theory, where the relationship between quantum K-theory and K-theory is the same as the relationship between quantum cohomology and cohomology. So as an additive, so as a Z adjoin Q module, we can tensor with the K-theory ring. This time we have power series instead of polynomial, because our K-theoretic Gromov-Witten invariants don't have to go to 0 eventually. So the degree d K-theoretic Gromov-Witten invariant is the sheaf-Euler characteristic of the structure sheaf of the Gromov-Witten variety. And these things, if you fix lambda, mu, and nu and let d grow to infinity, this goes to 1, not 0. So we have to allow power series, not just polynomials. But we can't quite use them as the structure constants, because if we did, we would not have an associative product. So instead, we define the quantum product to involve these capital N coefficients, where in the degree 0 case, it is a K-theoretic Gromov-Witten invariant. For higher degrees, it's recursively defined in terms of the Gromov-Witten invariant and the lower N structure constants. Here we'll have O nu star to denote the K-theoretic dual of O nu. So if you multiply by O lambda, in the K-theory, you get the Kronecker delta. Okay, My goal is to fully describe in the quantum K-theory ring the product when I multiply an arbitrary class by a hook class. What's already known? Well, in quantum cohomology, Bertram found Pieri rules for multiplication with special classes. Benedetti, Bergeron, Colmenario, Soliola, and Satilla found a hook multiplication formula. Buch, Kresch, Perpu, and Tamvakis found a puzzle formula. In K-theory, Leonard found Pieri rules and Buch found a Littlewood-Richardson rule. And in quantum K-theory, Buch and Mihalcea found quantum K-theoretic Pieri rules. But a quantum K-theoretic Littlewood-Richardson rule is not currently known. Right now, if we want to do computations in it, we have to reduce everything to be a product of the special classes, the rows and columns, and build it up recursively. Okay. What is the combinatorial interpretation of quantum K-theory? We can define this quantum poset to be the plane modded out by an equivalence relation with the northwest to southeast partial order. So, annotate, please. So, this point is the same as this point is the same as this point in our equivalence relation. Similarly, this point is the same as this point. And the northwest to southeast partial order says that as you go in this direction, you increase. So a quantum shape is a non-empty proper lower order ideal. You can describe an order ideal by describing its boundary. So I will draw quantum shapes by drawing the thick line that represents their boundary. In particular, any partition is an example of a quantum shape whose border happens to go through the origin. And so if we're thinking of it as an order ideal, we can think of it as all of this here. But we can also just think of it as a partition as like when it goes through the origin, it is a partition in our standard P sub x without a hat rectangle. Clear all drawings, thank you. Okay. So if I have a quantum shape lambda, I can define lambda shifted by d to be the shape obtained by shifting lambda southeast by d steps. So if lambda is on the left, lambda shifted by 1 is in the middle, and lambda shifted by 2 is on the right. It goes on forever in both directions. I've just drawn a part of the path. And we care about these because the basis element q to the d o lambda, where lambda is a quantum shape that's also a partition, where lambda is a partition, rather, corresponds to the quantum shape lambda shifted by d. So these are the combinatorial objects that describe the quantum K-theory. We have quantum K-theory Pieri rules. If we write P for the row and 1 up Q for the column, don't confuse with the quantum Q, please. And we can multiply an arbitrary class by the row or the column classes. You add on a horizontal or vertical strip. There's a sign coefficient. There's a binomial coefficient that involves how many non-empty rows or non-empty columns, as the case may be, in the skew diagram that there are. So these are the Pieri rules, and we can use them to find coefficients when you're multiplying by a hook class rather than just by a row or a column. I'll write A/B for the hook with A plus 1 boxes in the column and B plus 1 in the row. So like this is 2, 3. Why is it? Okay, stop. Thank you. Oh. Let's try that again. It won't stop drawing. Okay, there we go. So, this is A, this is B. So I'm ignoring the top left box that's in both the row and the column. Okay, and so in both K-theory and quantum K-theory, we can expand a hook class as a linear combination of row, column, row times column by using the Pieri rules recursively. And when we do it, this is what we get. It's a purely K-theoretic computation that holds true in quantum K-theory as well. From this point on, all of my multiplication will be in quantum K-theory. I'm going to leave off the star and just use juxtaposition to represent it. Okay, so applying the Pieri rules, what do we get? Well, when we multiply by a row and a column, adding a vertical strip and a horizontal strip in some order, what we've added on is a rim. We've added a skew diagram that has no 2 by 2 boxes. So any non-zero coefficient that shows up will have the skew diagram be a rim. Also notice that the coefficients care about the skew diagram. They don't care about exactly what the original nu and lambda were, and they only care about the skew diagram up to translation in our poset. So if our skew diagram happens to live in the standard rectangle of the Grassmannian, then we have a K-theoretic structure constant because the K-theory combinatorial interpretation lives entirely in the standard m by n minus m rectangle. If nu mod lambda is a broken rim, if any of these squares, little boxes, are missing, then it can be translated to be in the standard rectangle. For example, if this box were not here, and this was gone and this was gone, then it would be in the standard rectangle. And if we're missing any box in the rim, then we can translate it so that the box we're missing is exactly there. So only when we have an unbroken rim do we get a structure constant that's new to quantum K theory. An unbroken rim happens when nu is lambda shifted by 1, which means O nu is Q times O lambda. So if I can find that coefficient, then I've entirely understood the quantum K-theory multiplication because we already understand K-theory multiplication. And in fact, I have found it. If lambda is a quantum shape that has t corners, so this has 3 corners, for example, 1, 2, 3. Note that this point is the same as this point, so it's not an extra corner. If lambda has t corners, then I have a formula here for the coefficient of q times O lambda in the product O lambda OAB. If we do a change of variables, as shown on the bottom line, then we have this nice positive sum formula with the sign that we're expecting it to have that gives us the coefficient as a sum of products of binomial coefficients. How do I prove this? Well, write O lambda times OAB and expand the hook class as previously discussed. How do you reach Q times O lambda in the product? Well, you can't be adding only a horizontal strip or only a vertical strip. So this and this don't affect the coefficient of Q O lambda. They just give us zeros. Only this part matters. So when I'm using the Pieri rule and I'm adding a column and a row in some order, it has to be a maximum length row and a maximum length column if I'm going to reach the full unbroken rim. That means in the Pieri rule, when you're summing over all possibilities when you add a vertical strip or a horizontal strip, there's only one that gives us a non-zero coefficient on Q times O lambda, because there's only one way that you can add a maximum length strip. So if you just take the coefficient here from the decomposition of the hook, and then you take the signs and the binomial coefficients from the Pieri rules, we have a formula for the coefficient that I'm after. It's a alternating double sum of a triple product of binomial coefficients, but it exists. And from here we can work with it. So I've reprinted the lemma. It's the same as on the previous slide. And so if we do a change of variables, then the expression becomes easier to work with. We lose the explicit dependence on n and m. What's going on with this change of variables? Well, for terms in the lemma to be non-zero, we can't have m minus I being larger than t minus 1. So this gets us bounds on I and j. They don't actually start at 1, they start at something larger. So if we shift the indices down and shift A and B down appropriately, we've lost the explicit dependence on M and N, the parameters of our Grassmannian. And we have a nicer formula that computes the same thing. From here, it remains to show that this slightly nicer formula is in fact equal to the positive sum that I gave earlier.
15 minutes.
Thank you. And this we can just do. The inner sum, so this part, yeah, or so this part without the I minus one, because that doesn't depend on J at all. This part is a principle of inclusion-exclusion combinatorial identity. Once that's been resolved, you can do a double induction first over the minimum of A and B and then over T A and B all at once. And in fact, it completes the proof and these are equal. So I have found a positive formula for the coefficient of Q times O lambda in the product lambda times a hook. All of the rest of the coefficients we know from normal K theory. So in fact, I have completely described the product that I am after. Yeah, thank you.
Thank you very much. Okay. Great talk. So we have time maybe for a quick question.